Imagine being told that one of the most fundamental constants in all of physics, the speed of light, isn't actually something we've ever truly measured. That everything we know, everything we believe about this unbreakable cosmic speed limit might rest on a definition, not a discovery. Sounds impossible, even absurd, right? After all, the speed of light is exactly 299,792,458 meters per second. We're so certain of that number that we've used it to define the very length of a meter since 1983. But here's where the ground starts to shift. That number isn't the result of a direct measurement. It's a definition, crafted and agreed upon. And once you understand why that is, you might start to question everything you thought you knew about how we measure the universe. To grasp the problem, let's go back to basics. How do we measure speed? Simple, distance divided by time. If a baseball travels 100 meters in 5 seconds, we say its speed is 20 meters per second. But to do that, you need two things: a known distance and perfectly synchronized clocks at the start and end points. That's easy enough with slow-moving objects and high-speed cameras. But try doing this with a beam of light traveling a kilometer through a vacuum, and you hit a fundamental barrier. You can't be at both ends at once. You can't start and stop the timer from the same place unless the light returns to you. So we use two clocks, one at the source, one at the destination. But how do we sync them? Any signal sent to synchronize them also travels at the speed of light, which introduces delay, which is precisely what we're trying to measure. This leads to an astonishing realization. There's no way to measure the one-way speed of light without already knowing the one-way speed of light. It's a closed loop. Every attempt to work around it falls into the same trap. Send clocks together, synchronize them, then separate them. Einstein's theory of relativity tells us that moving clocks tick differently. Try to account for that, and you still have to assume something about the light's behavior. Put a mirror at the end instead and measure the round trip. Now you're only measuring the average speed there and back, not in one direction. Historically, even the earliest experiments like Fizeau's in 1849 only measured light on a round trip. He sent light between the teeth of a rotating gear to a distant mirror and back. When the gear turned fast enough, the light passed through a different gap on the return. Ingenious, but still a round trip. His result? About 313,000 kilometers per second. Close, but still not the one-way speed. That's the key detail. So why haven't we cracked this yet? Because every method for measuring speed involves synchronizing clocks at different places. And the only way to synchronize those clocks is to assume something about how fast the light travels between them. It's a paradox. To measure the one-way speed, you need synchronized clocks. But to synchronize the clocks, you must already know the one-way speed. And here's the twist that turns your mind inside out. Einstein knew this. In his 1905 paper, the one that revolutionized physics, he acknowledged that we define the one-way speed of light as being the same in both directions. It's not a result, not an observation, not a measurement. It's a convention. He put it in italics. By definition, the time it takes light to go from A to B equals the time it takes to return from B to A. That's not physics. That's a choice. So what if we're wrong? What if the speed of light is not the same in all directions? What if it's slower going out and instantaneous coming back? The laws of physics wouldn't break. As long as the round-trip time remains constant, 299,792,158 meters per second, every experiment still works. GPS, particle physics, astronomical observations, all of it remains internally consistent. That's the most mind-bending part. Reality behaves the same, no matter what we believe about the one-way speed of light. To illustrate the absurdity, let's imagine a conversation with an astronaut on Mars. Let's call him Mark. You send a message that takes 20 minutes to get a reply. Naturally, you assume it took 10 minutes to reach him and 10 minutes for him to reply. But what if the signal took the full 20 minutes to reach Mars and the reply came back instantly? You'd never know. Both scenarios give the same 20-minute round trip. The universe doesn't tell you which version is true. This opens the door to bizarre asymmetries in space-time. If light was slower in one direction and faster in another, it wouldn't violate the laws of physics. It would only alter your perception of simultaneity. What does now even mean for someone on Mars or a star 100 light-years away? If light is instantaneous in one direction, then Earth could be seeing distant stars as they are right this moment, while those stars see us as we were centuries ago. It's a viewpoint that completely rewrites how we think about cause and effect, about observation and reality. You might ask, why does this matter? Why dig into a concept that can't be experimentally verified and makes no practical difference? Because it shows us something crucial. Physics isn't just about measuring reality. It's about defining it. And some of our most sacred constants might be conventions dressed as truths, even when scientists attempt new ways to measure the one-way speed of light, like using ultra-high-speed cameras or massive lengths of fiber optic cable. They hit the same wall. The results always depend on assumptions about the light's behavior. The experiments, no matter how clever, always come back to round trips. Whether you're bouncing light back through a loop of cable or trying to synchronize clocks by firing pulses from a central point, the fundamental ambiguity remains. And here's a chilling thought. If the speed of light is direction-dependent, then even GPS, the backbone of our navigation systems, rests on a fragile assumption. Every satellite in orbit synchronizes with Earth-based receivers under the Einstein convention. If light travels at different speeds in different directions, every clock in that system would be misaligned. But we'd never know, because the measurements would still add up. We'd still calculate the same travel time, even if it wasn't true. What makes this even more astonishing is that it's all invisible to us. Light reaches our eyes, our instruments, our senses. We see it, record it, trust it. But we know nothing of its journey. Did it take 1 second or 20? Did it crawl or leap instantly? We just assume, and we have to, because we can't know. This is not a loophole in the math. It's not an experimental limitation that better tools will fix. It's baked into the structure of reality, or at least our understanding of it. As long as we accept Einstein's synchronization convention, everything works. But we must never forget, it's a choice, not a truth. So maybe this one unsolvable mystery, this unreachable measurement, is more than just a curiosity. Maybe it's a clue, a whisper that the universe isn't fully revealed yet, that our current understanding, however elegant, still hides deeper truths. Perhaps one day, the next great leap in physics, one that reconciles general relativity and quantum mechanics, will begin here, with the realization that we never truly measured